recording. And if you can, leave your videos on so I can see your reactions. People are still joining. But yeah, if you can, leave your videos on so that, I can see what you're thinking, maybe. And if you have questions, just unmute yourselves or type in chat. Any of that is all fair game. But it's been a while since we looked at any new content because all of last week was either a break day or the exam. So last time we actually looked at new content was last Thursday. So just a reminder, we tried to finish up chapter 10 last Thursday. And I said there's a few things that I wanted to talk about before we ended that I think are very important. So let's rewind you all the way back to, oh, I just realized you can't see me. There it is. All right, so let's rewind all the way back to the beginning of chapter 10, when we were talking about the fact that we needed to develop some theory to describe how particles move as waves. And we mentioned that we're going to make some postulates, right? Some assumptions that we're not going to prove these assumptions. They're just things that we're assuming are going to be true. The first of those was the fact that there is some wave function. There's some function that we call the wave function that we give the symbol psi to that describes everything about a particle. The second postulate was that fact that every observable, everything that we can observe has an associated Hermitian operator. The third postulate was that to observe something, it needs to set up an eigenvalue equation, right? Where the operator times the wave function returns a constant times the same wave function. The fourth postulate is everything must obey the time-dependent Schrodinger equation, right? H psi is equal to I H bar and derivative of psi with respect to time. Or in the case of stationary states, it breaks down to the time-independent Schrodinger equation that looks like this. If I'm missing any, let me know. But the fifth postulate was an average value of any observable is this integral right here, psi star times the operator times psi d tau, and that goes over all space that the particle sort of occupies. And that's sort of where we left off. The very last section in chapter 10 in your textbook contains two more postulates, but it's just sort of listed there without any explanation. And so we're going to go over those. So let's look at the postulate, quantum mechanical postulate 6, right? There we go. So according to the postulate number 6, it says that the set of eigenfunctions, make this a little bit smaller, for any quantum mechanical operator is a complete set of functions. That seems like a random statement, right? All of the eigenfunctions for any quantum mechanical operator is a complete set of functions. What does that even mean? Well, anytime we solve an eigenvalue equation, if you remember, so let's look at the Schrodinger equation for a particle in a box, right? This was the equation. When we tried to solve this equation, we found that there wasn't just one function that made this equation work. There were a whole bunch of functions. And so we label these functions with some number n, right? Where we said that n goes from 1, where n is positive integers. So there's not just one function that solves this equation, there are many functions. This, in fact, is true for any quantum mechanical operator. Let's say you had the momentum operator times, let's just say, some function f, right? To give you some constant times f. There wouldn't be just one function f that satisfies this, but a whole list of functions. We can label them with I. Anytime you solve these eigenvalue equations, they're going to be a list of functions. all of the functions that make up the entire set of functions that make up the solution is what we call a complete set. So complete set of functions. What do I mean by that? Well, let's say if we take all of these psi values and we put them into a set. So the first one would be psi 1, the second one would be psi 2, and so on. That's what we mean by they form a complete set. But what does complete means? Well, a complete set simply means, and of course mathematicians might have their own particular set of definitions, simply means that you can describe any other function with it. So it's complete in the sense that you can take another function and describe it in terms of that complete set of functions. What do I mean by that? So let's say you have some arbitrary function f, right? We know that all of the solutions to the particle in the box makes up a complete set, right? So we can take f and describe it in terms of that complete set. So we can describe it in terms of psi 1 plus psi 2 plus, and all the way to infinity. And to make all of these functions be equal to the function that we're trying to describe, we multiply it by these sort of coefficients. So these here are coefficients. And you could do this for any function. You could take any function and describe it in terms of other functions that are part of a complete set. So does that start to make some sort of sense by what complete set means? Yeah, maybe. Right. So if we want to simplify this, we could simply say this function f is the sum over all the possible values of n times the coefficient times the wave function. Here we use this wave function, that's a particle in the box wave function, as an example. It could be any function that's eigenfunctions of operators. This idea here is called superposition. Superposition. I'm going to talk about it a little bit more after we talk about the next quantum mechanical postulate. So the last one is quantum mechanical postulate. What number are we up to? 7, I think. And this states that if a given wave function psi is a linear combination of non-degenerate, remember degenerate means they have the same energy, but this is non-degenerate wave functions, or really any other functions. Let's call those new functions psi n, such that, hang on, my pen is starting to freak out here, such that we have this situation. So this wave function can be written in terms of this other wave function, right? Like this. Where psi n, I'm sorry, my pen is freaking out now, has eigenvalues. Let's write those. So let's say we're looking at some operator, let's call it just O hat to be general. Some operator O times this wave function gives us some, I don't know, let's say some constant Kn times the same wave function. Then the probability of observing Kn will be Cn squared. And I think this is listed probably in the exact words. Maybe the words are slightly different in your textbook, but it's just listed there without any explanation of what that means. So let's finish up with this is the superposition principle. All right, what does this all mean? Let's look at an example then. So let's say you have a particle in the box wave function for n equals 2. And my pen issue is getting really frustrating. But let's say this is n equals 2. This is the wave function, psi 2, for a particle in a box, right? We stated that any wave function can be written in terms of other functions if they form a complete set. So let's say we want to look at the position operator. And let's say there's some function for the position operator, and let's call this value A, returns some eigenvalue times the same position operator. The position wave function. Where here, we're going to treat this as the position wave function. Now, you're probably wondering what function is that, but again, right now we're not really concerned with what the function looks like. But if you want to imagine what a position wave function might look like, right, it might look something like this. For now, let's draw it as a little block, right? If my pen would let me draw a block without. So let's say that's the position wave function psi of A, where this value of x is A. Where's this going? You're probably asking. Well, we stated that any wave function could be rewritten in terms of these other wave functions. So we're going to state that this wave function psi can be written in terms of all the different values of A times some constant, we're using A here, times the wave function A. All right. What does that look like if we were to draw it? Well, let me draw this again. Here is our wave function that we're trying to replicate. And we're going to do this approximately, even though this equation is an exact equation. I'm going to do it approximately, and hopefully you get the gist. So we said that one of these little phi wave function, we're going to just draw as a block, right? So, here it'll probably be this block, that block. We're adding up all of these different blocks, right? And hopefully you can see that you can write one equation in terms of another. And for these blocks on top, the value of C, the constant, would probably be positive. And for these set, C would probably be negative. But we can take any function and write it in terms of another. And this time, we wrote them in terms of position wave functions. Why is this useful? Well, remember when we had the particle in a box wave function, and we applied the position operator for it, we didn't get back a constant times the same wave function, right? Because this does not set up an eigenvalue equation. And we were like, okay, you have a particle in a box, you cannot observe the position. And that was true, but we also went about finding the average position, right? Using this equation. So at the time, I hope you were thinking, well, if we can't find a position, but we can find an average position, how do we find the average position in the first place? Because to find an average, you need to find a position over and over again and take the average of all the numbers, right? Well, in reality, you can find the position. It's just not, it wasn't straightforward, so we pushed it to the end, and your textbook kind of ignores it completely. But according to the last quantum mechanical principle, if you were to apply the position operator to this wave function, it's like applying the position operator to all the wave functions that made up the wave function, because we said that this wave function can be written like this, right? And each one of those has its own value. Where did we write that? Its own eigenvalue. So so here's the weird thing. When this happens, the wave function is gonna pick one of these green bars. It's gonna pick one of them and return that value. Which one it picks is arbitrary, but the probability of getting picked is CA squared. The probability of getting picked, right? So if you try to observe the position, right, the wave function thinks it's a combination of position wave functions, and then it's going to pick one based off of C squared. So that's why the higher positions get picked more likely than the lower positions. And so when that happens, the wave function then becomes the position wave function. So whatever wave function we started with, we apply the position operator, and then it picks a position wave function and goes with that eigenvalue. This whole process here is called wave function collapse. The wave function collapses to a different wave function depending on what operator we're looking at. This is one of the freakiest things in the whole quantum mechanics realm. And we talked a little bit about it a couple of weeks ago, probably too much about it a couple of weeks ago. But yeah, this is wave function collapse. Anytime you try to observe something, the wave function collapses to one of the wave functions for that observable. So in a sense, wave functions are always sort of collapsing between things. Does that make sense? Or no? So why is this useful? Let's use a simple example. Let's say this wave function is made up of just two other wave functions. And I'm going to use simple examples here. So let's say some wave function is made up of 1 over the square root of 4 times some function we'll call a plus 1 over 3 square root of 3 over 4 times some wave function b. Right here, what I'm trying to write is phi is equal to C1 times A plus C2 times B, right? A and B are other wave functions for some other observable. And let's say we take some operator O and we apply it to wave function A, we will get some observable A times the wave function. And similarly, if we do the operator O on wave function B, we get some constant B times the wave function B. My question to you is, what do you get when you apply O to wave function psi? And what do you get when you try to find the average value of O for wave function psi? Well, how do we go about doing that? If you're trying to find the operator O on wave function psi, it will pick one of the two, right? And the probability of it picking one of the two will be the square of the C coefficient values. So the probability to observe A, right, which is if we collapse to the A wave function, would be the square for that C squared, which in this case, it's 1 over the square root of 1 over 4, which is just 1 over 4. And then the probability to observe, oh, come on, pen, be nice. observe B is basically C squared for B, which would be 3/4. And I just chose those numbers to work out nicely that way. So that's when we're trying to find a specific value for an observable. But what about the average value? Well, the average value for the operator will be 1/4 times A plus 3/4 times B, because the probability of observing A is 1/4. The probability of observing B is 3/4. So the average value would be the probability times what? The observation. Does that make sense? Or not? Let's do one for practice, and maybe by doing it, we have a feel for what this looks like. So let's say the wave function is a superposition of 3 states. We're going for 3 states now, and I'm going to write what they are. So psi is going to be square root of 1/5 times some state alpha plus square root of 3/5 times some state beta plus the square root of 1/5 times some state gamma, right? That's our wave function. Psi is not an eigenfunction, sorry, of some operator. We'll call it S. So psi is not an eigenfunction of this operator, but alpha, beta, and gamma are. And I'll write what you get when you use that operator. So if you apply that operator on alpha, you will get, let's say, A times alpha. You apply the operator on beta, you get B times beta. And you apply the operator on gamma, and you'll get C times gamma. We're just making up those as symbols. My question to you is, what is the probability that the wave function collapses to gamma and you observe C? So C is the observable that you get. And then for the second part, what is the expectation value of the operator? So spend some time on working on this. It shouldn't take too long. Let's see what we get. You can type your answers in chat when you think you have an answer. And if you have questions, please ask. Nobody with an answer yet? Yes. Well, for part 1, yes. So what is the probability that the wave function collapses to gamma and you observe C? It would be the square of the coefficient in front of that. So it'd be the square of 1/5, which would be square of the square root of 1/5, which would be 1/5. That's why I write the coefficients as square roots, so that when you square them, you get nice numbers. So that is the probability of you observing C because the wave function collapses to gamma. What about the average value of this operator, the expectation value of the operator? So for I, it would be the square of the square root of 1/5, which is just 1/5. What about number 2, the average value of the operator? So this is the probability. So I'm not sure if you're not answering because you're not confident or because it's just so easy.
Is it just on like a weighted average? Or
yes, it's a weighted average, essentially, like what we did up here. So the average value, right, for S would be the probability of observing A times A plus the probability of observing B times B and so on. So it will be 1/5 times A plus 3/5 times B plus 1/5 times C. That's the average value.
Other question, will the probabilities always add up to 1?
Yes, it should. So if you're wondering about this, where are we? We said that this wave function would be a sum over all the wave functions times a coefficient times a wave function, like that. If you add up Cn squared for all the n's, you should get 1. And again, this only works if all the wave functions are nicely normalized. If they're not, it becomes a little bit more complex. But yes, the probabilities should all add up to 1, because this is true by definition for normalized wave function. So does that, oh, maybe I should leave that on the screen. So does that make sense? Or not make sense? It's this, I think the reason the textbook skips over this so much is because it's not as intuitive. But really what this is saying is that every time you try to measure something, the wave function collapses to a wave function that's actually an eigenfunction of the thing you're trying to measure. It's a weird concept to think about, but if you're trying to measure the position, the wave function collapses to a position wave function. If you're trying to measure momentum, the wave function collapses to a momentum wave function. And whichever one it chooses to collapse to is random, right? It just has a probability associated with it. For example, here we measure the probability that it collapses to the gamma wave function. There's also a 1/5 chance that it collapses to the alpha wave function and a 3/5 chance that it collapses to the beta wave function, but it's all just random chance. So this is where Schrodinger's cat comes in. Like, you could have a wave function that's, let's say, the square root of 1/2 times living cat plus square root of 1/2 times the wave function of the dead cat, right? And you could, there's some, like, let's say, check if living operator on the wave function, it's not an eigenvalue. So you can't just apply the check whether it's living or dead operator to the wave function. But if you check whether you use the living operator, I'm calling it, it's just something I'm making up. On the living operator, you get, living times the living wave function, right? If you use the living operator on the dead wave function, you get dead times the dead, because those are eigenvalues, right? So what happens if you try to check whether the cat's living or dead? Well, it chooses one of these two based off of their probabilities, right? It might choose the living one with a half a probability. It might choose the dead one with a half a probability. But until we try to use the operator, we won't know which one it is. And that's the whole idea behind Schrodinger's cat. Now there is a way to turn the cat back from dead to living. And I think in the very beginning of the semester, Andrew, I think, mentioned something about like polarization, and you can like flip polarizability. So, but let's not get into that. Way too cool a thing to cover in lecture. Um, but there is a way to turn the cat back living. So yeah, there we have it. Wave function collapse and the superposition principle, not covered at all really in your chapter. The other thing that I wanted to talk about, do we have any questions on this before we move on?
Can you go back in the, like, once you have your new wave function, can you go back in the other direction to get your original wave function?
Yes.
Same method?
Yes and no. Depends on, you need to do something to force it back. Like you need to try to make an observation of some sort to force it back. The Schrodinger's equation, these wave functions are eigenvalues of the energy, and particles are always evolving according to their energy. So it will slowly turn back into that anyway, right? As it evolves over time with the time-dependent Schrodinger equation. But if you try to measure another position, it will not change position. It already decided which position it's going to be, and that's it. Does that make sense? But like I said, with the case of a living or a dead cat, you can change it back by trying to observe something else that's a different eigenfunction and then coming back. A good example of how you can do this is using position and momentum, because we know you can't observe both at the same time, which means that they each have different functions. Let's call this one F, and let's call this one G, and we'll give it J. All right. So if you try to observe a position, it will give you a position. But then if you try to observe the momentum, it will change the wave function to momentum. Then if you try to observe position again, it might choose a different spot this time and give a different position, right? So you can actually change where the particle is. Of course, there are rules in how fast it can change and stuff like that, I think, although nobody's really sure about how fast these things really happen. Like how fast does the wave function collapse? These are all really great questions. Some of them that nobody knows the answer to. And some of them probably requires explanations that are way too long for this class, especially since your textbook thought it wasn't even worth studying, which I disagree. But if you do, please come to me. We can talk about it and geek out about it afterwards.
Dr. Chulai, can you
Yes.
scroll up a bit?
Sure. How far up? Is that good?
A bit higher. Yeah,
Is that
right
good?
there. When you said like the sum of n and then like cn squared equals 1, what does that mean?
If all the psi n's are normalized, then this gives the total probability, which is 1, right?
Okay, thanks.
You're welcome. So yeah, that basically says all the probability must add up to 1. So there are two ways to finding average values, right? We did the fancy integral, or we can get the average value if we know what states our wave function is a superposition of. And obviously this way seems much easier, right? At least to me. The other thing that I wanted to briefly mention, your textbook, I think, talks about it only in passing though. Correspondence principle is a correspondence principle, right? Now, we know that quantum mechanics is the theory of everything. Not the theory of everything, but the theory of how things work, how things behave. So you might be wondering, why is it that classical mechanics work for things at sort of our macroscopic day-to-day lives, And really what the correspondence principle states, so the correspondence principle states that the behavior of quantum mechanics reproduces classical mechanics in the limit of large quantum numbers. So there is no like point where, for example, you need to switch from classical mechanics, from quantum mechanics to classical mechanics. Really, if you use the same equations for for quantum mechanics, but the quantum numbers n, m, whatever they are, gets larger and larger, it starts to resemble classical mechanics. So it's like a transition. It's not like you use quantum mechanics here, you use classical mechanics here. No, it's like a slow transition where eventually the equations of quantum mechanics will give you results that look like what you would get with good old classical mechanics. And here's a quick example of that. So I always like to use the, I don't know, n equals 2 wave function for the particle in the box, right? If we were to square this, so this would be the probability density, whereas this is just a wave function, right? What did we get? We got the fact that there was a node here, and then the probability is highest here, and then it varies, right? But in classical mechanics, if you had a ball in a box bouncing back and forth, the probability of it being anywhere in that box is pretty even, right? Like there is no node or anything where the ball just disappears, right? So this is classical physics. Well, the correspondence principle says that if you go to very, very large numbers of n, quantum mechanics should look like classical mechanics. So let's look at it. So let's say we have the same box, but instead of n equals 2, let's use a very high value of n. I don't know. I'm going to draw it, whatever number that is. If I were to take, so this is our wave function, right? If I were to take the probability, right? It would look something like that. Now the probability is starting to look kind of like a constant, like it would in a classical case. There's still some nodes, but they're getting smaller and smaller. Like the regions for the nodes are getting smaller and smaller. And everything is starting to look more and more flat. Whereas here, the probability sort of changes across the box. So this is an example of the correspondence principle. It's just something I thought we should all sort of know about because, you know, it's where quantum mechanics start to become less important because we can just use classical mechanics to describe the system, because why go through all the headache of doing a quantum mechanics equations when a classical equation could do. So that's a correspondence principle. Another idea that your textbook skipped over completely is this idea of commutator relationships. Let's say we said that for the position and the momentum wave functions, and they're more than just position wave functions, they come in pairs. There is no same function that can describe both, and the same eigenfunction that can describe both. And that when that happens, we say that you can't observe these two things simultaneously, right? And based off of what we learned about superposition, right, that means that if you have a wave function and you apply the position operator, you get basically a position wave function, right? And then if you apply the momentum operator on this position wave function, it changes again to a momentum wave function. So every time you apply one of these two, it changes the wave function. And so you can't really see both of them at the same time because the wave function is always changing. If you can apply, let's say, some other general operator a to some function f, and you get back some value a, and you can apply some operator b to some function f, and you get back a different value b, you can observe these two things at the same time because the function doesn't change, right? So the eigenfunctions are eigenfunctions of both operators, so you can observe them both simultaneously. We can represent sort of this idea in what we call a commutator. So a commutator for two operators, commutator, looks like this. Let's say you have two operators, A and B. The commutator looks like, this is how you represent it. In square brackets, A comma B. And when you're trying to evaluate it, this will be A times B minus B times A, right? If the commutator of A and B is equal to 0, then you can observe both A and B at the same time. Right? If A comma B, which again, remember, it's A times B minus B times A, is not equal to 0, then you can't observe both A and B at the same time. Let's look at an example. And please stop me if you have any questions. But let's say A and B are the position and momentum operator, right? And we want to apply them to some wave function. So we know that the commutator for the position and the momentum operator would be A times B minus B times A, right? So let's say we apply this to some wave function, which we're going to call psi. So we're going to be this operator minus this operator times the same wave function, right? Okay. So let's look at this part, the x times the wave function minus this times the wave function, right? That's what it breaks down to. Let's look at this part over here. So what this says is you're first applying the momentum operator to this wave function. So you'll get a value for the momentum, let's call it k, times the momentum wave function. Let's just use this for the momentum wave function, right? And then you're applying the position to that wave function. So you get a position wave function and a different value of k. Let's call the position wave function that. Here, it will be the opposite, right? First, you get a position wave function with some different value of k. Sorry, let's do it this way. Then you get a momentum wave function. Let's call it k4. So the order matters because the wave functions keep changing. So this doesn't come out to be 0. If you want to see it done mathematically, we know that x operator is just x multiplied by whatever comes after it. And the momentum wave function is minus IH bar ddx. So if we take x dot momentum versus momentum dot x, right, times some wave function, we get x multiplied by negative IH bar ddx. And over here we get negative IH bar times ddx of x times the wave function. And hopefully you can see that the differential times the wave function times x is different from the differential of x times the wave function. I know those words sound very similar, but like d dx of x times sine x is not the same as x times d dx of sine x, as an example. Basically, when you use those operators, the wave functions will change, and so you can't do both of them at the same time, so the commutator comes out to not be zero. So all you have to do to figure out whether something is going to give you can observe something at the same time or not, is to look at the commutator. If the commutator is zero, then you know, oh, these two things can be observed. If the commutator is not zero, then you know that these two things cannot be observed at the same time. Does that make sense? Blank stares. No, maybe.
So does the a and b in brackets have to be applied to the wave function first to equal zero?
Yes.
Or, okay.
Yeah, you have to apply it to the wave function to know. All I want
so
you
like,
to
sorry,
yeah,
if you go up to the purple text, like where it, like second row, if bracket a comma b equals zero, would there really have to be a psi in there?
you can evaluate a commutator without let's see. That's more of a semantic in how you want to write this. To evaluate it, you do need to apply it to a wave function, but it doesn't matter what the wave function is. You can put a placeholder in there to evaluate.
Okay, thank you.
All I wanted everybody to take away from this is what's called a commutator. If it's zero or not zero, it tells you whether you can observe the things at the same time. That's all I want you to take away. Anything more than that is extra. Sounds good? Yes. All right. It's more stuff that's not in your textbook. And if any of these is a little bit too much, let me know, because it's not in your textbook. I can point you to other sources, or we can go over them again. But they're typically, what I want you to take away is just like one thing. What does a commutator look like? What does it mean when it's zero? What does it mean when it's not zero? I don't necessarily want you to like go over into math or anything like that. But the next thing that I want to talk about was Dirac, or sometimes called bracket notation. I don't think your textbook has this at all. So, but it's not really, it's very easy. In fact, it looks very nice once you get it all together. In Dirac or bracket notation, we're gonna write, I'm not gonna go into detail about why this is done so, but you're gonna take any function and instead write it as a line, that function, and a right angled bracket like that. So this here, these two symbols around the function, that's known as the ket. So for example, if you have the wave function in bracket notation, that wave function would just be written like that. The complex conjugate, right? Conjugate. We usually write it as psi star. Well, what we're going to do is write a left angled bracket psi on a line like that. And that will be the bra. Right? Notice that I got rid of the star. I just wrote it without the star. So you might be wondering, why are we going through the trouble of writing all these extra little symbols to represent the same things, right? Like here, we're adding 2 different symbols to this. Here we're adding, technically there are 3 symbols here versus 2. We're making things more complicated. But together, they represent integrals. So basically, if I wanted to write a complicated integral like psi star psi d tau, right? That's a lot of things to write. I can just write it as the bra with the wave function times the ket with the same wave function. And now it becomes so much easier to write. So automatically, when you put a bra and a ket together, it means an integral. So sometimes you might see things written in terms of bracket notations, but they're not really that complicated. For example, the time-independent Schrodinger equation can be written as, right, h bar psi, but instead of psi, they just put it in a ket, is equal to energy times the same wave function psi. They put it inside of a ket, right? Once we see things like that, we shouldn't like really be too like, oh, what are those extra symbols? They're just alternative ways of writing this whole thing. I'm gonna make it in a different color so that it stands out. But more than just writing integrals like this, it's also useful for other integrals. For example, we know that the average value of, let's say the average value of some square of some operator can be written as psi star, the square of that operator times psi d tau, integrating over all space, right? That's a whole handful to write. We could write this as the bra times the operator. In this case, it's a squared times the ket, like that. Now, you're probably wondering when I said that this is the average value, where these angle brackets, why are we using angle brackets? But this is why. Basically, somebody decided that we can just take these parts and just rewrite that whole thing like that to simplify it. But that's where those angle brackets came from when we were writing average values. But yeah, that's how you can rewrite the expectation value of something in bracket notation. Does that make sense? So I just wanted you to be aware that such a thing exists so that when you see it somewhere else, it's not surprising. So today, so far, we've covered quite a few things that weren't in your chapter 10, and I just want to summarize those before we move on to the next bit. So we talked about the 6th quantum mechanical postulate, which is the idea of superposition, where any wave function can be written in terms of any other wave function, right? And then quantum mechanical postulate number 7 talks about the idea that if you want to make an observable on a wave function when you can't, it's not an eigenfunction, the wave function will collapse into one of the possibilities based off of the coefficient c squared. That's the probability of making that collapse. And that's how you make that observation. And we walk through an example of the particle in a box wave function collapsing into a position wave function. We did some practice with that by finding average values and probabilities of collapse and how that, and we talked about how that ties into Schrodinger's cat. We talked about the correspondence principle. That is when the quantum numbers get larger and larger, things start to resemble classical mechanics. We talked about commutator relationships, where if the commutator is 0, then two particles can be observed, two observations can be made at the same time. If it's not 0, then basically Heisenberg's uncertainty principle rules. And then finally, we talked about Dirac notation or bracket notation, where there's a ket, right? That's just a function. There's a bra, that's a complex conjugate of that function. You put them together, you get bracket, which represents an integral. And then you can like put operators in between them and do anything that you would normally with integrals, except it looks much easier to write. It's much faster to write. Any questions on any of those so far? Nope. All right. So with that, that will bring us to the end of all the things that I wanted to cover in chapter 10. And at this point in the course, you know everything about quantum mechanics that you need to know. And I can send you off in the world and you can do whatever you want with it. Everything else from here on out in the course is applying those things that you learned to specific situations and to gain some insight about how specific things work. So we're going to go over some of those specific situations, but know that everything, all the principles, everything that we're going to work from here on out follows from what we covered before. Now, so theoretically, you can be like, oh, okay, I know everything. I can stop the course here. But we're going to go over some of those examples. And the first one of those examples that we're going to go over is called the harmonic oscillator. So we're going to apply the equations of quantum mechanics to specific situations. Why these specific situations? Because they give us some insight into how atoms and molecules behave. And the harmonic oscillator is one of those models that's going to give us some insight into how matter behaves. Now, if you've already started the Jupyter notebook that's due at the end of this week, you would see that we already looked at particle in the box, right? And I said that the one-dimensional particle in the box gives us insight into how conjugated polyenes work in terms of their energy levels. That's for like 1D particle in a box. If you looked at the Jupyter notebook so far for this week, you would see that a three-dimensional particle in the box start to give us a good idea of atomic orbitals, right? They're not quite exactly the same, but they're starting to resemble this idea of atomic orbitals, three-dimensional particle in the box. Harmonic oscillator is going to give us insight into how molecules vibrate, right? Molecules are always vibrating and stuff like that. The harmonic oscillator is going to give us insight into how that happens. So our objectives for sort of this section is going to be to understand the motion of a classical harmonic oscillator, to find the wave functions and energies of a quantum harmonic oscillator and we're going to model diatomic molecules. That's just molecules with two atoms. So diatomic molecular vibrations, actually, let's do that. As quantum, that's quantum harmonic oscillator. I just shorten that to HO. And then finally, we'll learn how to easily integrate odd and or even functions. So this is going to cover a few of the things, first few sections of our chapter 11. Now, before I get in, I want to show you an animation quickly of harmonic oscillators. So let me stop this for a second and pull it up. All right, so there we go. And this is going to be part of your next Jupyter notebook. So if we can imagine, sorry, there we go. Let's have this load. So if we can imagine a spring, right, stuck to a wall, one end is stuck to a wall, the other end has some mass on it, right? And you displace this spring, the spring is going to go back and forth, right? That's a harmonic oscillator. That motion, that periodic motion going back and forth like that on a spring or something, that's harmonic oscillator. You can think of a spring, you can think of a pendulum, any of that stuff. So let me get back to, there we go. Okay, so in a harmonic oscillator, so this is a classical harmonic oscillator we're looking at. So in a classical harmonic oscillator, we can think of it as the wall. There's a spring attached to some mass going back and forth, right? On the x-axis, we're going to call the starting point 0. And we know that the force on a spring is minus kx, right? So basically, if x goes in a positive direction, the force becomes negative and pulls the mass backwards. If the particle goes in a negative direction, the force pushes it forwards. The potential becomes half kx squared. So if we're modeling the potential, let's say this is our axis, the potential is half kx squared. And you can think of instead the particle just going back and forth in this well. Both descriptions sort of help you give an idea of what's happening with a classical harmonic oscillator, right? So in this setup, there's a few things that I want you to realize. There's such a thing as called the period of oscillation, which is basically the time it takes to complete one full oscillation. So one full oscillation. So you can think of it as the time it takes for this spring to go forwards, backwards, and back to where it started, or for this ball to go like roll forwards and then backwards again. So that's the period. And then another thing that I want you to focus on is the frequency. So there's a frequency of oscillation. And the frequency is 1 divided by the period, which is going to be equal to 1 over 2 pi, because it's making a complete sort of starting where it begun kind of thing, times the square root of k over m. K here is the force constant. So in a classical harmonic oscillator, we have a period, we have a frequency, we have a force, we have a potential, we have all the things that we need. M here is the mass. In case you weren't sure, this is K here is a force constant. So let's look at this again. So I'm gonna, you know what? I'm gonna share that whole screen so that I don't have to go back and forth. So am I sharing my screen? No. Okay, there we go. So here we see that whenever x is positive, the arrow here points to where the to the direction of the force, right? So when the distance is negative, the force is positive, and vice versa. Here we get the position, here we get the force. In the bottom here, we're thinking of it in a different light now. Up here, it's force and distance. Down here, it's in terms of potential, right? So the right is the potential. And as it moves left and right, the potential energy gets higher. In the middle, the potential energy is lower, which means the kinetic energy is the highest, right? So as it changes, the potential energy would be changing into kinetic energy. And so V is the potential energy, K is the kinetic energy. And this is just a classical harmonic oscillator as it goes sort of back and forth. Yeah. All right, so let's now move on to quantum mechanical harmonic oscillators. So just remember, this is the equation for the frequency, right? If we wanted to rewrite this classical equation here for the frequency in terms of the force constant, what would the force constant be? So we have this equation, 1 over 2 pi times the square root of k over m. If we square everything, we get the frequency squared is equal to 1 over 4 pi squared, right? 2 squared pi squared. And then this becomes k over m. And then I want to rearrange this to solve for k. So k then would be equal to 4 pi squared mu squared m. In case you didn't know, we call this nu or nu. Depends on who you ask. That's the frequency. So this is the force constant rewritten in terms of other things. And we're going to use that in a second. Now let's talk about the quantum mechanical harmonic oscillator. Whenever we're trying to solve a problem, we need to solve the Schrodinger equation, right? Solve the Schrodinger equation. We said that earlier, all of quantum mechanics is about solving the Schrodinger equation. We know the Schrodinger equation is this guy. H psi is equal to E psi. So to solve this, we need to write the Schrodinger equation. We need to expand out H. So what is H? Well, we said that H is always going to be equal to the kinetic energy plus the potential energy, right? We know that the kinetic energy never changes. It's half mv squared if it's classical, or negative h bar squared over 2m times d squared dx squared, right? That's k. And we have the potential energy. But we know what the potential energy is because it's the potential energy of the harmonic oscillator. We stated it all the way back here. It's half kx squared, right? So the potential energy is here. Here's half kx squared. Remember, x in classical terms is the same as x in quantum mechanical terms, right? The operators are the same, so we don't have to worry about that. So the Schrodinger equation is, if we write this all out, it's negative h bar squared over 2m times the second derivative of x. I'm going to use big V like that, plus half kx squared times the wave function is equal to the energy times the wave function. All right, so there's a few things now I wanted to do. I'm going to take this and multiply the whole equation by negative 2m over h bar squared. So I'm going to multiply everything. Hang on. I need to create some space. So we'll do it this way. We'll multiply everything by minus 2m over h bar squared so that I can turn this first term here into 1. So that becomes d squared dx squared, like that, right? This term here becomes negative, right? Negative times positive becomes negative. Half times 2 becomes 1. So on the top, we got mk, right? This m times that k divided by h bar squared from there. times x squared, right, from there, times psi. And on the left-hand side, it's e times the stuff here. So it's negative 2me over h bar squared times the wave function. I'm going with somewhere with this, I promise. Okay, we have k here, but earlier we said that k can be written like this. K is 4 pi squared nu squared m. So I'm going to do that. So I'm going to substitute k. So what did I end up with? D squared dx squared minus m times 4 pi squared nu squared m. So it's 4 pi squared nu squared m. So m times m becomes m squared. And all that is over h bar squared. There's x squared. There's the wave function. And on this side is negative 2me over h bar squared wave function. Everybody with me so far? This whole thing is a lot of, these are all constants. The mass, 4 pi nu h bar, they're all constants. So I'm going to say let this constant alpha be equal to 2 pi m nu over h bar, such that when you do alpha squared, you get 2 times 2 is 4, pi times pi is pi squared, m times m is m squared. Basically, you get squared of everything, which basically is exactly what that thing is. So if I do that, I can simplify this whole thing to look like this. Alpha squared, x squared. Here's wave function, and this is minus 2me over h bar squared times the wave function. And then finally, I'm going to rearrange this to put everything on the same side. So rearrange to bring everything on the left-hand side. We got d squared dx squared minus alpha squared x squared. Then this negative, when we bring it over on the other side, becomes positive. So it's positive 2me over h bar squared. All of this is multiplied by psi, right? And then if we bring it everything on the left-hand side, everything becomes 0. And this is what we need to solve. So I'll wait for a second while everybody gets up to here.
Can you scroll up some, please?
Sure.
Thank you. That's good.
So at this point in your textbook, there's about 4 or 5 pages of how do you actually solve this. I'm not going to do that because I don't want to say it's a waste of time because I'm being recorded and then somebody's going to put this up on YouTube and be like, Professor Chalai says it's a waste of time. But it is a waste of time. Mostly because to solve this, it's all math. And mathematicians have solved it years before, decades, probably centuries before, probably decades before quantum mechanics even thought of it, right? Here you have an equation where the second differential of that function minus some constant squared times x squared of that function plus some bunch of constants times that same function is equal to 0. Earlier, when we started this, when we were doing stuff, we were like, what function, when you take the derivative, you get back some constant times the same function? That was easy to think about, right? Like e to the x, that works. When you had second derivative, we're like, oh, sine of x, that works. But when you have something as complex as this, it's not easy to be like, oh, what function would work there? Because it's not intuitive. You can figure it out by doing a bunch of derivations and stuff, right? That's in your textbook, and if you want to follow along. But honestly, I don't care if you know how to figure out what function actually fits this equation. I will just tell you what function fits this equation because mathematicians have solved it. The function that fits this equation, and remember, there's always more than one function. There's a whole class of functions that forms a complete set. So we're going to label them with some number. X is exactly this. It's alpha over pi to the 1 over 4th power times 1 over 2 to the nth power times n factorial to the half power, which is square root, times this special function, which I'm going to talk about. So it's a function of alpha to the half power times x, times this exponential part of the function, x, right? Where n is 0, 1, 2, 3, basically 0 and positive integers. That's the answer. That's what function fits this equation. The energy that fits this equation that you get out would be the same number n plus a half times Planck's constant h, not h bar, just h, times the frequency nu. I want you to recognize here, n goes from 0 now. When we did particle in the box, n started at 1. Now n started at 0. So don't mix those two up. And this guy here is called a Hermite polynomial. Named after the same Hermite guy that we have Hermitian operators from. Fun fact, he didn't discover these polynomials. He wrote them down 50 years after the first guy who discovered them, but somehow it gets named after him, not the guys who first discovered it. So we have a Hermite polynomial. All of these stuff, all of this beginning part, that's all the normalization. So this function is normalized, and all of this stuff, all these constants here, is just to make sure it's normalized. So it's a normalization times this Hermite polynomial times this exponential part. We call it an exponential decay. It makes sure that the function goes to 0 when we go to positive and negative infinity. These Hermite polynomials here's what they look like, right? So for n equals 0, we're going to write them in terms of this variable we're going to call xi, pronounced, I think, like this, xi. So for n equals 0, this is just 1. For n equals 1, this function is 2 times xi. For n equals 2, right? This becomes 4 times xi squared minus 2. Again, exactly how we came up with this is not important. Just know what they are so that we're able to plug these in. But at xi equals 3, this becomes 8 times xi cubed minus 12 times xi. And I'll stop at 4. But this continues to infinity, really. Although I don't know how much people have actually figured out what the exact expressions are. So that's what the first 4 Hermite polynomials are. Right? I want to point out that instead of xi, we need to substitute alpha to the half power times x. So these are just general Hermite polynomials. We need to remember.
Sorry, is that 48 for that middle term?
Yes, 48 times xi squared.
Okay, thank you.
So we need to remember that we need to use xi as alpha to the half power times x whenever we're doing our substitutions. right? The other thing that I wanted to point out was that the powers of xi depend on what the powers of the polynomial are. So for 0, we get xi to the 0, which is just 1. For 1, we get a term that's just in terms of xi. For 2, we get a xi squared term. For 3, we have a xi cubed term plus other terms. For 4, we have xi to the 4th power plus other terms. Right? So I just wanted to point that out as a little curiosity. The second thing I wanted to point out is for even numbers or odd numbers of n, we only have even numbers or odd numbers of powers of xi. So xi 1, n equals 1, we only have xi. N equals 2, xi squared. N equals 3, we only have xi cubed and xi. No xi squared or anything like that. Only odd powers of xi. Xi to the 4th, we have xi to the 4th. N equals 4, we have xi to the 4th and xi squared. No odd powers of xi. That will come in useful in a little bit, but just recognize that that happens. So with that, what do I want you to do with this? Well, I want you to be able to use these to write the wave functions and energies for specific values of n. So write what the n equals 2 value is for a quantum mechanical harmonic oscillator. How would we go about doing this? Well,
Hey,
I'll
Dr.
show you.
Chulai, just so you know,
Yes.
we're out of time.
Oh, thank you for that. Oh man, I got too engrossed in these things. All right, we'll pick this up on Thursday. If you have any questions, let me know. I know we covered a whole wide range of topics today. So yeah, if you have any questions, let me know. But yeah, we'll pick this up on Thursday. Otherwise, enjoy the rest of your day.